Okay, hello, welcome back. So in the last couple of lectures, we discussed the kinematics of particles and the dynamics of a system of particles. And so moving forward, we're going to get more involved in detail interworking of system of particles and rigid bodies. So one of the important concepts that often shows up and people discuss is the idea of degree of freedom. So let's first define it. So degrees of freedom. So it is a definition, the minimum number of variables or numbers needed to fully describe the configuration of a system. So very simply, how many numbers do you need to tell me where the system is? And I can fully understand the configuration of a system. To better understand those, maybe look at a few examples. So for now, pretend we have a three-dimensional space and a particle in that space. So this is a particle, meaning that the particle itself doesn't have any dimension. So it's left and right and top and bottom really doesn't make any difference. So for that particle, the only thing I need to tell you to know where it is in this space are three numbers, x, y, and z. And just knowing these three variables, I can fully describe my system of being one particle. One thing to note here is that the choice, this three number is rather fundamental. So you cannot describe this system with fewer than three numbers, and more than three, you don't need it. But the choice of those three numbers are not unique, not necessarily arbitrary, but they are not unique either. So for instance, instead of I tell you the x, y, and z positions, I can tell you some angle, some distance r, angle phi, and maybe another z. So instead of describing my system in a Cartesian space, I can describe it in a cylindrical space or a spherical space. And notice that in all of those, we need three numbers, either x, y, z, r, phi, and z, or r, phi, and theta for spherical. Okay, and that means the system is system of one particle in a three-dimensional space, has 3 degrees of freedom. Similarly, now let's take a look at the box, a rigid object. So this was a particle. Let's look at rigid object. Object. Up. It's missing something. So I can still tell you where the object is. So I still need at least three numbers. But now object has dimensions. So my cell phone, if I want to tell you exactly how my system is set up in a space, not only I need to tell you where it is, but also its orientation. So these are all in this object is in the same location, but it has different orientation. So in other words, I need to also give you three angles in three space. So three positions, three angles, I need 6 variables. So it's a 6 degree of freedom system. Maybe another example. So again, I have a particle. Now I have two particles. Now my system contains two particles in 3D. So for one of them, I need three numbers. For the other one, I also need three numbers. So this is in total two particles, 6 degrees of freedom. Now things can start to be a little interesting. Let's look at the last example. Not last. I have more examples. I have the same two particles, but now let me connect them with a rigid rod. Now how many degrees of freedom is this? I still need to define at least one of them with three numbers. But to describe the position of the second object, I no longer need three numbers. Two would be enough. For instance, I can look at, I don't know, a coordinate frame and describe the two angles, this angle and that angle, to tell somebody where the second object is relative to the first one. So I have 3 plus 2, that is a 5 degree of freedom system. And again, notice that these are particles, so really I don't need to define the rotation about the axis of the object because it's meaningless. The object doesn't have any dimensions along that. So every time I touch my screen, I get a dot. So this is very tightly related to the idea of constraint. So remember, I needed 6 numbers to define the two particle system. Now I have added a constraint that the distance between the two particles is fixed. So that's a known number. I don't need to tell you as the system moves around in space, that number is fixed and we can ignore that. So one number is already given. That means one number or 1 degree of freedom is reduced from the system, and now we go from 6 to 5. Okay, maybe a couple more examples and we should be done. Let's look at the mechanism. So I have something called a 4-bar mechanism, something like that. I'm gonna pause here for you to think how many degrees of freedom this system has. How many numbers do you need to tell me for me to understand where the system is or how the system is configured? So the answer is this is a 1 degree of freedom system, 1 degree of freedom. And this is in 2D, by the way, on a plane. So the reason is that if you give me just one angle of, for instance, the first link relative to a reference, the rest of the mechanism is fully defined using that single known angle. So as I push, as the angle change, I don't know, for instance, this link goes a little to the left, it's going to pull the other link down, and the system doesn't have anywhere else to go. So it is completely defined just one number, and that means the system is 1 degree of freedom. Now, let me remove this constraint, the last attachment point to the ground, and look at this. So we have one link goes here, another link goes here, another link comes here. And this last link is loose in the space. Now this system became a 3 degree of freedom system. Now I need to tell you this angle is, what that angle is, and what this angle is, to be able to fully tell you how the mechanism is configured. So I need three numbers, 3 degrees of freedom. Again, I want to draw your attention to the idea of constraint. By constraining the end of this mechanism to be at a certain X and Y position by pinning it down to the ground, I have removed two numbers you need to tell me where the X is and where the Y is of the tip of this mechanism. So if I remove that, you still, from the 4-bar mechanism, you now need to give me two more numbers for me to understand where the system is. And that means it's now a 3 degree of freedom system. So I hope it is clear, and feel free to have more examples for yourself and try to check the degrees of freedom of those systems. One thing that can help is, so if we have a particle in 2D, these are known information in 2D. So I only need to know X and Y position. So the degrees of freedom of this system is 2. If I move to 3D, I need X, Y, and Z, so 3 degrees of freedom. If I have a rigid body in 2D, how many is that? Pause and think. Answer in 3, 2, 1. So this one is also 3 degrees of freedom, because now I'm looking from above on a 2D plane. I have one object, one rigid object. I need to tell you where X and Y position of the object is. Oh no, keep. Okay. No. This. So this is a new laptop system I'm working with. It's a little clunky and I cannot change some of it because I don't have admin access. So whenever I touch the screen, it does something. Sometimes shows this dots, sometimes it goes to the next slide, a little annoying. So anyways, a rigid body in 2D space has 3 degrees of freedom because I need to know where it is and its orientation. So as the object rotates in that space, I need to know that angle too. And we saw rigid, don't do this, rigid body in 3D. And we saw it was a 6 degree of freedom system. Okay, these are useful because when we have a system of n freely moving objects of any of these kinds, so the total degrees of freedom is k times the degree of freedom e of each times the number of objects of that kind that we have. So if we have 2 objects in 3D, that would be 6 total degrees of freedom. All right, so now that we have discussed the idea of degrees of freedom, in the next video, we will be talking about the idea of constraint, which is very important. Constraint is what puts these free-floating objects and attach them together to make a useful system or mechanism. And we'll be talking about that and the idea of generalized coordinates instead of normal coordinates like X and Y, how we can generalize that idea. Okay, until then, I'll see you soon.